Okay, welcome to today's YAPC webinar. The title of today's webinar is Spanning and Connecting Key Techniques and Design Challenges of Jianghehui Landscape Pedestrian Bridge. The speaker is Honglei Wu from China. I'm the moderator. I'm the professor of Tongji University and also vice chair of the Chinese group of YAPC. So welcome to all our participants. First of all, I'd like to introduce a short introduction of IFC. Let me share my screen. Okay. The full name of IABAC is International Association for Bridge and Structural Engineering. Its mission is to exchange knowledge and advance the practice of structural engineering worldwide. It has members over 100 countries, and we have national members and individual members. The YAPC is a scientific technical association comprising members in 100 countries and counting more than 60 national groups worldwide. It was founded in 1929 and has its seats in Zurich, Switzerland. President of APSI at the moment is Tina Vision from Denmark, and the elect president is Harsha from India. So APSI deals with all aspects of structural engineering. And here the goals, the objective tasks is to promote cooperation and understanding among all those concerned with structural engineering and related fields by worldwide exchange of knowledge and experience, and to encourage awareness and responsibility of structural engineers towards so- societal needs, to exchange actions necessary for progress in structural engineering, and to improve and foster cooperation between organizations having similar objectives. So for this purpose, the association will organize its conferences. It has two conferences every year. It has a congress in autumn and a symposium in spring. And it will publish high quality journal SEI, the Structural Engineering International. And it publishes books reflecting the works of technical groups we call the SED, and creates technical groups as required by new needs and technology progress, offers opportunity to join activities within national groups at EPSI, offers a program for young engineers, and present annual awards. So this is kind of activity. This year's Congress was in Ghent, in Netherlands, in Belgium, and next year's symposium will be in Copenhagen, in Denmark. So besides the physical meetings, we have also e-learning programs, including webinars and lectures, YAPC Academy also. So today's it's an online seminar is called webinar. So uh, it is in one of the e-learning program, and you can find all the webinars in the YAPC website. Um, you can download from that website all the webinars videos. So this webinar will be also recorded. And we have award. YAPC has awards. We have YAPC People and Paper Awards, and projects and awards for projects and technology. So we have different kinds of awards. Today's webinar, this bridge is in the finalist of pedestrian and cycle bridges this year. It will be in Switzerland, in Zurich, in next month, to have the winner of all the awards. And today's webinar, the speaker is Hongwei Wu, holds a PhD in structural engineering from Tongji University and is a national first-class registered structural engineer as well as a chartered structural engineer. He currently serves as Deputy Chief Engineer of Tongji Architectural Design Group Co. Limited and is an off-campus supervisor at Tongji University. He work his work focuses on the research and design of complex structures, including super high-rise buildings and energy dissipated structures. He has been recognized with numerous awards, such as the First Prize of Shanghai Technology Invention Award and the Excellence in Structural Engineering Award from the Institute of Structural Engineers. He has also published over 80 academic papers and 5 books. And today's the title of his presentation is Spanning and Connecting Key Techniques and Design Challenges of Jianghehui Landscape Pedestrian Bridge. So let's welcome Dr. Honglei Wu to give this webinar. I will close my stop the sharing. Okay, please.
Thank you, Professor Xu. Hello, everyone. It's my pleasure to have this chance to give this speech for you. I will share a bridge. Recently, we finished in Hangzhou. Okay. Can you see my PowerPoint?
No, not yet. Yes.
Yes. Okay.
Yep.
My presentation includes 4 parts. The first one is project overview, including the bridge location, the bridge architecture concept, and some information, and what we are facing, the challenges we may design this bridge. The second part is the bridge structure scheme, including mechanism and composition and some parameter comparisons we did. And the third part is specialized design, including the wind tunnel test, pedestrian comfort analysis and test, and seismic design, and some detailed design. The last part is about construction process and some site photos. This is a site picture of Jianghehui Bridge. This bridge is located in Hangzhou, China. The architecture design of this bridge is Zaha's Institute, and the structure concept design is designed by Arab. We are the Tongji Architecture Design Institute, and we are the local design institute department, and we do all of this bridge design and construction review. This bridge is designed in 2021, and the bridge is finished in 2024. Now you can see this picture. This bridge, along this bridge, there is a very large river, which is Qianjiang River. It's about 600 meters wide. And this a little small canal, we call it the Jianghehui Grand Canal, is very famous in Chinese history. The left picture is this Jinghang Grand Channel. This channel is about 1,800 kilometers long from Hangzhou to Beijing. Beijing is the capital of China. And this canal is built in 2005 years ago, when is in Qing Dynasty. And it is by man-made canal. But now this Grand Canal is World Heritage in World Heritage list. This bridge is in this very unique and important position place. So this bridge has some meaning about the history between the modern and old time. And also this canal have very important function for now for the busy shipping. And also in Hangzhou, this bridge will be the landmark. You can see in the old time, Hangzhou is known as West Lake. For now, it will transfer to the Changjiang New Era. So this bridge is very important landmark in this place. So the architecture Zahat is a very talent designed group. They designed a very important aim for this bridge. They called it threading the like the needle, which means seamless the city. It has two meanings, including seamless history, which means the bridge connects the old time and the modern time. And also, this bridge has very important function. It's called the seamless city. This bridge spans three disconnected shores and connect to five urban districts. It has a very important function to this place. Uh, because of that architecture is Zaha design group, they like to use a very unique and curved shape geometry in this bridge. So the bridge geometry is also very complicated. It has three bridge continuous each other, including the West Arch, which is 145 meters long, and the Middle Arch is 79 meter, and the Eastern Arch is 156 meter long. And all the decks is connect with each bridge. You can see from the west to the east, the deck connect to each arch. So the deck will help to bearing conflict forces in this deck. And also because this bridge is near the shore, the foundation is not very good. So we have to design this bridge use a self-balance system. So at each bridge, in each bridge, we used a tie cable to balance the arch truss in the bridge. When we designed this bridge, we faced many challenges, including system level, such as arch. This arch is inclined, and three arches continuous but not in one plane. And there's support is complicated. It's a symmetry boundary, and because the bridge height is has strict limited, so this bridge it has a small width to span ratio. The deck is very wide; it's up to 6 meter wide for the deck, and have many functions, including walking, cycling, and marathon. And also for the side view reason, this deck is a single side suspension. And because of this complex geometry, the structure's components is also complex, including irregular air plate, twisted arch pair, and also the arch deck joint. And because it's in Hangzhou near to the Yellow Sea, so the wind load is large. According to Chinese code, the design flutter wind speed is up to 46 meter per second, equally to 14 levels typhoon, according to Chinese code. This is some more detail about this bridge. You can see the three arches are continuous, but not in one place. So every two bridge will create very large and unbalanced force in arch pair. And because this bridge is the top of this bridge is limited, so the raise to span ratio is small. So this the truss arch is shallow arch, leading to very large truss. And for the boundary is symmetrical. One side is fixed to the ground, and the other side is placed on the slide bearing. So we use this tie cable to balance this arched truss. And this bridge deck is very special because it has many requirements like marathon event and cycling use. So the width of this deck is up to 6 meters. And also for a better side view, this deck is single side suspension. So people in this place can see the Qianjiang River. And because this cable tension to these airplanes does not pass through the deck center, so under gravity, it will create a very large torsion in the deck. Also because of the complex shape, the every airplace is different size, different angle, and different forces in the airplace. And also, the architecture has strict requests for the manufacturing. So high prices data need in this airplanes. We provide this data to the manufacturers and to the construction group to make these airplanes. And this is a twisted arch pair. You can see there are every arch pair have to bearing two arch truss and cable tension. Because the two arch is not in one plate, so there is a very large torsion in the arch pair. And at the same time, at the end of the bridge, the arch deck joint in here, just I said before, the deck will transfer a very large torsion at the end of the arch and deck joint placed. And we use a very large cantilever beam to transfer this torsion to the supports. This is some structure system about mechanisms. And for example, we use one west arch as to say, can see under the gravity. Uh, this arch is self-balanced in arch plane. The gravity load will transfer from the deck to by the hand cable to the arch, and the arch will transfer big trusses to the end, and we use tie cable to balance this truss from the arch. So the foundation's force will be largely reduced. Horizontal forces is only just a vertical load for the foundation. And we do many comparisons and many calculation about the arched inclined angle, arch section, and weight to make sure the combined force of the arch weight, self-gravity, and the suspension force from the deck to lined in the arch place. So the arch, although this arch is inclined, the forces in the arch is mainly the axial force, and because we have tie cable, so we can balance this truss. Therefore, all the force in the arch is in one plate. And for the deck, the vertical component of the hand force will balance the deck weight, gravity. But because this force will not go through the deck star, so there will be a very large torsion. And for the horizontal components, the force will balanced by the shear and axial force in the deck and transfers to the end of this bridge, and in this side it will transfer to the other bridge, and will go into the third arch end for this deck force. This is some detailed design about the member of this bridge. Can see for the arch member at the foot place, the arched member will up to 4.3 meters high and 4 meters wide. We use six size shaped member, and in the top of the arch the member will be smaller. Is about 2.8 meter high and 2.6 meter wide. And the in the arch member is very complex because we have to anchor two cables. This large one is a hanger cable to support to hang the deck, and the small cable is the suspend cable we use to hang the tie cable. And the thickness of this member this arch member is about 14 millimeter in the foot place and 32 millimeter in arch top. The material is we use the steel about Q420 MPa. In this bridge, we have three types cables. The first one we call the tie cables, which is at the back of this bridge, used for balance the arched truss. The tie cable, each arch has four tie cables. Each tie cable's diameter is 140 millimeter. There is about 7,000 kilonewton in each tie cable. And the second cable we call suspension cable. This one for to hand the tie cable. This diameter is small. It's only 60 millimeter. It will be have about 1,200 kilonewton in each suspension cable. The third type of cable we call hanger. It's used for the hand deck, and there are two diameters. Small one is 18 millimeter, large one is 100 millimeter, and the fourth is about 3,000 kilonewton. All of the cable coating is Gofen for corrosion protection. The material of this cable, we use the strength up to 1,513 ampere. For the deck material, we also use high-performance steel Q420, and the cross-section of the deck is about 6 meters long and 1.37 meters high at the end, and at the top is 1.29. The thickness of this deck is about varies from 70 millimeter to 24 millimeter. We add intermediate webs to form a single box double cell cross section and enhancing the torsional stiffness and overall stability of the deck. And in structure concept scheme, we and Arab did many calculation about this bridge, including the raise to span ratio and the inclination angle, and study on some cross section. And we compare with some typical inclined arch bridge. For example, in China is Tanshishan Pedestrian Bridge, and Queen Elizabeth Bridge in Austria, and Gateshead Millennium Bridge in United Kingdom, and Federal Garden Pedestrian Bridge in Germany. All of the four bridge each has simple bridge geometry, and they have a strong bridge pair. The force can directly to the foundation. And we compare some parameter between these five bridge. From the arch span, we can see Jianghehui Bridge is very long, up to 156 meter, and the deck wise is also very is big, now less than Gateshead Bridge, and for the raise to span ratio, the other four bridge is about 1 to 3, but in our bridge, it's up to 1 to 7, which means we will have very large arch truss. And we also compare the inclination angle because our bridge is large and is heavy, so with the inclination angle can't be very large. So our bridge is more strict than other bridge. And for the cross-section type, because architecture wants our bridge is unique, so we use hexagonal section, which is six size section. We compare different parameters about like span, uh, like incline angle, and cross section type. So we design the finally parameters for this bridge. Because this bridge, footbridge is large and it's near the big river. The wind load is strong, so we did some wind tunnel test in Tongji University, and we compare different wind situations such as uniform flow field and turbulent flow field. And this model is 1 to 49 full bridge scale. And this is some details. We also simulate the handrail in this bridge. According to the wind tunnel test, our bridge, this bridge, the critical flutter wind speed under all test conditions in both turbulent and uniform flow fields was greater than 77 millimeter per second, which is about level 7 typhoon. Uh, in our code, we just have to satisfy the level 14 typhoon, which is about 46 meter per second. But as you know, in this time, many more large typhoon happened in near same place in China. So we have to make our bridge more stronger. And we about the comfort of this bridge, we according to a Germany standard, there are mainly two sensitive frequency about vertical vibration. The small one is 1.25 hertz. And we calculate our bridge. There is a 11th model shape, and the vibration of this west bridge, west arch and deck, the frequency is 1.5 hertz. So we calculate the acceleration response about this model, and we can see the vertical acceleration is exceed to the code, which means tuned mass damper is needed in this bridge. We added 10 TMD device in west and east bridge to reduce the vibration. And after putting the TMD device in this bridge, the acceleration will decrease up to 1 to 10 from the past. And we also do many site tests, vibration and comfort tests. And from this picture, and we do some test, and the vertical peak acceleration of the west arch span structure is only 0.19 meter per square second, and the horizontal peak acceleration is only 0.09 meter per square second, which will satisfy the CL1 level, its highest level in German standards. And for the seismic design in Chinese code, we have to face two seismic requirements call it E1 level, which means the structure should remain elastic in 475 return years earthquake action. And in E2 level, the cables should remain essentially undamaged, and local minor damage may occur in critical structure components in 2000 return years Earth action. And we put some steel blocks along the longitudinal and transverse in this bridge to prevent the deck falling. And also we put some metal dampers in the bridge to make some plastic energy dissipation during E2 earthquakes. For the airplanes, just I said before, the geometry is very complicated, and so we have to use a way to make some accurate and safety airplanes. And we used Rhino and Grasshopper software to confirm each airplanes. There are three types each place. The easy one we call small airplanes is only an sexual tension force in these small airplanes. For some tall airplanes, there has tension and bending in the airplanes. So we use continuous tension fridge in these airplanes, and for the compression frame is welded. And the complex one we call twisted airplanes. It has tension, bending, and torsion in these airplanes. We calculate all of the airplanes, and we can see we also consider 5% out of plane loads in these airplanes, and the maximum stress is about 200 MPa. And because architectural form gives the arch pair section spatially continuous and twisted airplanes, pairings, so the force in this arch pair is very complicated, including two arch compression and cable tension, and which will make very large torsion in this arch pair. So we set many internal diaphragms and stiffeners in the arch pairs to make sure the safety of the arch wall panels under combined stress condition, and on the other hand, ensure the reliable transmission of the tie tension. Also, we calculate the different load condition of this place, and the steel stress is about 226 MPa. And for the arch deck joint, the arch foot is also a very critical part of the entire bridge, which we have to make sure the coordinated work of the arch force and the deck, because the deck torsion will be transferred to the arch member and to the support. And we also holds many ankle diaphragms in the arch member to transfer the tie cable's force. And we also use three crossed beam to transfer the decked torsion force to the arch. And we use UHPC material to this place to enhancing structure stability. This is some calculation. Okay. The last part is construction uh, and site photos. This is the bridge installation process. It has 8 steps. The first one is the deck lifting and welding. Uh, this is the deck. The second process is the arch lifting and welding. And this arch is lifting. And the third is to install the hangers cable between the arch and the deck. And the fourth is to install the tie cable and the suspension cable of each arch. And next, we removed the arch scaffolds. And at this place, this tie cable will have passive tension. Next, we adjustment of the hanger cable. We make some force, make some force in this hand cable, and next we remove the remove of the deck scaffold. In this time, we will create some more passive tension in the hanger cable and in tie cables. At last, we adjustment of all the cable force, mainly the hanger cable, to make each cable's force is more event. This is the finished part of this bridge. We can see the tie cable have to make sure there is enough height space for the ship. This is a finished bridge, and the other bird view, and from the top view, and from the human view. Okay, that's all for my presentation. Thank you.
Okay, thank you, Dr. Wu, for your very interesting introduction of the aesthetical and technical design details of the very unique pedestrian bridge. So we'll find some questions. So I have two questions. So why only the East Arch has the suspension cable? Because the West Arch, you don't have suspension cable. So why only East Arch has suspension cable for the tie cable?
Yes, we have suspension cable in Eastern Bridge. uh,
But why not West? You only has
yeah,
suspension cable.
we have the suspension cable in Eastern Arch and the Western Arch. All the two arch has suspension cable for hand tie cable.
Oh, so I saw this picture that only the
Sorry, maybe it will be
oh, it
overlapped.
has suspension cable. So okay, okay, okay.
Yes,
You
yes,
all have suspension cable for tie cables.
yes,
Okay, okay.
yes.
And the second question is how about the thrust of the of the mid arch because you have suspension cable for east and west arches. And what kind of structural components for the thrust of the mid arch? I,
Okay.
I, uh,
Yes, for the mid arch, the span is small and the raised span ratio is 1 to 2. So the thrust in this middle arch is not very large. But because the foundation is not very good, so we also put a tie cable in the middle arch. The tie cable is underground. But
ah,
this tie cable is small.
but you already has this tie the the tie in underground to take the
Yes, yes,
thrust.
yes,
I don't know.
yes,
Okay,
yes,
okay,
yes.
okay, okay, okay.
Mm.
And so the so could you please give us some details of the design of the foundation of the main foundation of this three span? I mean that is span three continuous, but not in the same plane of the bridge. The two major uh, foundation. What kind of foundation?
Ah,
Piles?
yes, yes. This foundation is very typical. It's just the pi foundation
Ah,
because most of the torsion and shear force is transferred by the raft, not transferred by only the vertical force will transfer by the pi foundation, pi.
so
Okay.
there's no inclined piles. It's only vertical piles.
Yes, yes, yes.
Okay, okay. So the suspension cable can take the thrust of the east and west arches, and the tie underground can take the thrust of the mid arch. Am I right?
Yes,
Okay, okay. So you don't need any inclined piles to take
yes,
the uh,
yes.
horizontal
Uh,
forces.
yes, because the canal government administration have very strict, very high requirements. They don't allow us to make any pipe inclined to go into the canal. So we only be allowed to transfer the vertical force in the foundation. Okay.
Okay, so how did you construct in the construction on site? How did you build the horizontal? That means that the underground ties for the mid arch.
In in the middle arch, actually, they're not. They don't have many horizontal force in the middle arch, cause the middle arch is,
In Ireland, yes.
yes, yes, the middle arch we don't have many horizontal force because we put tie cable on the ground to balance the horizontal force.
Okay, okay,
And for the each side large arch, we used tie cable. So there were not many large horizontal force in these two bridge pairs. Okay.
okay.
Mm.
So, do you have any lightning design for this bridge?
Yes, we have, but the picture not very beautiful, so I didn't put
Do you
you,
have any materials to show us?
material. What material? Sorry.
I mean, some kind of slides or pictures for the lightning design of the bridge.
Lining.
Lightning
Sorry.
design of the bridge in the evening.
Yes, I don't have the picture, so sorry.
Okay. Let's check if we have any questions from the audience. So the stability design, I mean the statically stability. So what is the uh, first first order of this buckling for the bridge?
Oh, okay. First buckling. The first buckling of this bridge is out of plans deformation of this bridge.
Ah,
Okay.
okay.
Yes. Yeah,
The mid
the large
arch,
one, the west arch.
arch.
Yes, the west arch. The first buckling model is out of plans deformation.
Okay. So what is the cost of the bridge?
About 1 point. Sorry. It's about six about eight hundred 80 million RMB. 80
Okay.
million RMB.
So the participants, you can post your uh, questions uh, here if you have any question about this bridge. So comparing to the you mentioned different bridges in UK, in Germany, in other cities of China. So what is the most significant characters of this bridge? Uh, Let us know about what you think. What is the most significant design characters of this bridge?
Yes.
What can make this bridge unique?
I think there are three parts. We in this in our bridge is very special. The first one is you can see for the fourth bridge, the geometry is very uh, typical. It have very good geometry of this bridge. It have not more reasonably raised to span ratio for this for bridge, but our raise and span ratio is very narrow, and which means we have a very large arch force. The second is also like Tanshishan Bridge is in the in the mountain, but it have very good foundation condition. So the bridge force can directly transfer to the foundation. Uh, Also, like this Gateshead bridge, it has very large span and wide bridge. Also, it has a strong foundation. But in our bridge, we don't allow to transfer the horizontal force in the foundation. So uh, we have to use more strong tie 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 cable tie cable for our bridge, and this tie cable is above the river. So we have to use suspension cable. So which means in our bridge, the horizontal force resolution is very unique in this project. So it has many type of cables, uh, and the last one is our construction process is very complicated. Because this deck it goes through the it's under the bridge, so we have to uh, make this deck first, and also there are many cables. And also just like the tie cable, it's a very large force, so we can't use active ways for in this tie cable. So we have to care, carefully uh, uh, in construction process to make passive tension in the tie cable. And you can see there are about three or four processes to confirm the finally tie cable force in this bridge. And also because we are in the very important place, the Grand Canal, you can see in this picture, the ship is very busy from day to night, so we have to carefully use as uh, use less car use less scaffolds as possible. So which means this arched bridge connects every part of this bridge member is very long. It needs a strong, large this device of this machine to lifting to this bridge, this arch member to the scaffold, and because the geometry is also complex, so it's very hard for the people to welding this bridge. Okay.
Okay.
Mm.
My last question, uh, because you mentioned that the cable force you call that passive, that means it is kind of reacted from the weight of the arch. You didn't tension that suspension, the tie suspension. Am I right? You didn't uh, tensioning the tie. It only take the reactive force. You call that passive force from the arch weight.
Oh yeah,
So
I can I see most of the ports in cable in tie cable and hanger cable is made by passive tension. But at the first, when the tie cable and the suspension cable is installed, some pre tension, which is active force will be uh, transfer
introduced
in
to
high
this.
cable. It's about yes, it's about 10 to about 15% of the total cable tension will be pre tensioned in the tie cable. At the second and third is just the passive tension in a tie cable.
Okay, my question is that you have some horizontal force left for the piers because the cable is a flexible component. It's not as a very solid
Yes,
tie. So it has some elongations because of the tensioning force. So I mean that the pier will take the thrust force. So you mentioned that there's no inclined piles, it's only vertical piles. So what about the horizontal forces left for the piers? It's
yes.
not big.
Yes, it's true. This arch pair, which means it's not there is some horizontal force in each pair, but it's small. It's not very large because we as end phrase, we also adjustment of the all cable force, which means for this tie cable, at last we also give this tie cable more tension in this tie cable to reduce this horizontal force in the arch pair.
Okay. So the time is so it's 9 o'clock. So well, thank you very much for the webinar and wish your design will win the
Thank
award
you.
in November. So thank you very
Thank you.
much, Dr. Wu. Thank you again. So, and thank you for all the participants here online. So I'd like to close the webinar. Thank you again.
Thank you.
Bye bye.
Bye bye. See you.
I see.